Good afternoon. Welcome to the video lecture about the human eye. So I'm just going to basically touch on some eye corrections based on lenses that we learned about and talk about some other challenges that lenses pose for people doing research or people, for eyes, for example. Of course, I'm an astronomer, so I'll give you some astronomy examples of images and the distortions that come from lenses that are kind of troublesome in astronomy. And, some of the research that I actually physically do is to correct these aberrations to make my images look more clean, because more clean images means you can see better into the universe. So let's talk a little bit about the human eye. Now, a lot of you have more background in biology than I do, so I'm just going to throw that out there. But I do want to just talk a little bit about the eye and how it works. So, right here we have the diagram of the eye and some of the listed, features of the eye. So the cornea is this, call it a flap. It's not really a flap, but this is right over the eyeball right here. You also have the iris, which, kind of allows the amount of light that gets into your eyes. So if you've ever seen, especially, I think, my favorite example of this is Jurassic Park, when they take the flashlight and they shine it right into the eye of the Tyrannosaurus Rex and the pupil gets real small. Yeah, that's to protect the eye so that you don't have too much light damaging, the cones and the rods that are in the back of the eye. In fact, I'll just go right to the back of the eye. So the retina is a place where we have lots of receptors to light to help process the light and understand it. Now, there's a special part in the back of the eye called the fovea where there's just more of these receptors. So, of course, taking the light and focusing it with the lens will allow us to kind of, generate an image and see it appropriately. There's also this little spot right here which has no light receptors, so that's our blind spot. So there's an exercise in the next slide to find it. But that's right where the light falls, where you actually can't interpret it because there's nothing there to collect data from. So, of course, the biggest focus is this lens right here. By adjusting the lens more or less, we can focus light at far distances and close distances, which is pretty incredible. So that's kind of what the lens does for us. It allows us it adjusts the lens to account for far things and close things. Now, with a camera, they do that. If you ever see the camera kind of zoom in and zoom out, they change the length of the focal, they change the length of the, what is it officially? The length between the focal point and the lens. And when that happens, you can change the image and make a more sharp image. But with the human eye, they actually do it with the cornea, which is kind of amazing. So we don't see our eyes going back and forth, right? So this is a fun little exercise to find the blind spot. So I have the directions right here, but if you close your left eye and you hold this about arm's length, so I'm about arm's length, so you cover your left eye, and you can move forward and backwards, and all of a sudden that X will actually disappear if you stare right at the dot. Ooh, it's right there. It's really crazy. It looks like the dot's completely gone. I'm sorry, the X right here is completely gone. All I see is the dot. And that's my blind spot. It looks like a white piece of paper. It's actually really kind of creepy. You should try it out. But like I said, the retina is full of these things called rods and cones, named for their shape. They actually don't look like a rod and a cone. I'll show you real examples, but that's kind of where they came from. But the rods allow for intensities of light, so like really strong light versus really dim light is kind of not controlled, but received by these rods, and the perception of color are the cones. So this is what they actually look like in real life. So if you notice, they're kind of rod-shaped, and these are, well, not really cone-shaped in my opinion, but you get the idea of these rods and cones. Now, there are different types of rods and cones, and they're sensitive to a specific, color of light right here. And more or less, when you have this thing called color blindness, I forgot to include that. Let me see if I can grab that really quickly. Red, green, colorblind. So you might have even heard of this before, but let me just throw that in there. So when you have these color blindnesses, there's various forms of color blindnesses. Obviously, you can have a complete color blindness and just see black and white. And that's because your cones are not working properly. All the recepting of, all the light receptors for color are not working, or whatever the condition is. Again, I'm not a biologist. That's color blindness, so you see black and white. But sometimes certain cones and cones won't work properly, and you get this thing called color blindness of colors. So you can kind of test right now if you have this color blindness. Right now, let me see if I can move this. There we go. So right here is a red and green shape, and inside this shape is a figure 8, and I'll trace it out for you. So there's an 8 in red dots surrounded by a bunch of green dots. Now, people with red and green color blindness can't actually see or distinct this this red shape in the middle of this green dot right here. So you can actually test this out if you see this, kind of color blindness. Now, there's other forms of this, but this is probably the most common type that I know about. I had a friend that actually had this, and playing games like Sorry, where there's red and green, was kind of, and blue was kind of tough. So, moving forward, some of the things that we talked about with lenses is that it can correct by changing whether or not you want to diverge the light rays or converge the light rays, and all has to do with, your the defects in your eyes, that is. So I am actually nearsighted, although I have the farsightedness here. But actually, let's talk about the farsightedness because it's on here. So what happens is your eye is actually too diverging. So it takes the light rays and doesn't allow it to focus right at the back of the eye, which is where the light receptors are. We call this farsightedness. So this is for people who can't see close. It's farsighted because it's far beyond the eyeball right here. So how do you correct for that? Converging lenses. You take that ray, and instead of having it go too far, you kind of converge it a little closer like this. So to correct for farsightedness, you use a converging lens. So your cornea is actually just not, round enough. It's actually too flat. So, or your eyeball's too short. There's a couple ways that this can actually distort your image. But, so people who have these glasses, you can tell because you can take their glasses, and if they start to magnify, like a magnifying glass, you'll see that they actually have farsightedness. So actually I don't. I already just told you that, but I could kind of play with this a little bit. But if you kind of look at this, the image never gets larger, so I'm not farsighted. It's kind of hard to see with it, but you can definitely play with your glasses like this. So nearsightedness is what I have. I can't see far distances because what happens is they after it gets to my eye, it doesn't focus on the back of my retina. So this is the defect. This is my eye right now. So the light rays actually converge right here and not on the back of the eye. So because of that, I need something to kind of stretch out my rays so they get a little further. And that's what they use, a diverging lens. It's concave on both sides. That's why it's called concave, but it's also known as a diverging lens. So remember the properties of diverging lenses. It's always an upright image. It's always smaller and reduced. So that's why you can even look at my glasses and kind of see that. So when I wear my glasses, it takes the rays and spreads them out farther enough so it now hits and reaches the back of the eye. So these are just some, examples of this. I'll move myself over here where you can see that. So the uncorrected version versus the corrected version. So for nearsighted, like I am nearsighted, I need a diverging lens, and for farsighted, you need a converging lens. A couple quick other, defects in vision include astigmatism. So this is, you might have heard it, I actually have astigmatism in my left eye. It just means that my left eye is not perfectly spherical, and because of that, it causes the light rays to not focus in one point, but actually break away a little bit. So it makes things blurry because you have two focal points. They, remember, a really sharp image is all on one point. So it's really hard to do this. So how do they do it? So my lenses actually are not perfectly symmetric. They're slightly asymmetric to account for the curvature, the non-spherical curvature of my eye. Obviously, you will not be able to notice that with my glasses at all, but that's, of course, the prescription that I have. So, you know, when I got my contact lenses, they said, you know, this won't account for astigmatism because the reason why is contact lenses are spherically made. They can't change the size or the shape or the curve the way that your glasses can, because your glasses you can make, you know, their glasses are pretty much handmade with the lenses, but with contacts you can't do that. So I wear contacts and I still see better than without my glasses, but it's not as perfect as my glasses because contacts are spherical and astigmatism is not. So try to put a spherical contact lens in a football shape. It doesn't fit very well, so it doesn't work. But this is kind of a visual of that. So if you see the left image, you see that you have a really sharp image versus the astigmatism. So this, of course, is a really, how should I say, this is really, what's that word? Emphasized or really dramatic here. Obviously my eye, I don't see like this, but if it were really bad, this is how it would look. So the last thing I want to talk about is aberrations, so defects in the lenses themselves. So if it's a really thick lens and it's not perfect, you'll see that you have this thing called spherical aberration, where you can see here in the left image all the rays point to one point, where on this side they all kind of point in or come to a point in different places. So because of that, you don't get a purely focused image. You get a blurry image one of that. This is a form of aberration, but of course there's lots of different ways to correct for it depending on the type of aberration. So the first aberration type is actually called spherical aberration, which is actually what I just showed you recently. But you can correct for this by using a combination of lenses to kind of shift each of these rays into the spot that it needs to be. So this is a pretty challenging but doable approach to changing the image so it's sharper. So this is what it looks like for spherical aberration. It's supposed to look like a dot, but notice if the light is not focusing in one spot like this dot, you get the light in all different spots. So you get a kind of cloudy version of this. Because I'm an astronomer, this is what it looks like. So part of my job is to take images maybe looking like this with lots of cloudiness, and then taking the aberration out so it's a little more clear. And of course the reason for doing such a thing is that then all of a sudden you have, oh look, you have a star over here where you couldn't see it before. So getting this image resolution is actually pretty important. The last aberration is chromatic aberration. So with chromatic aberrations, what happens is all the light rays are actually separated due to their wavelength, and because of that, they cross the principal axis at different locations. So what you get is a really interesting effect. This is not really an eyeball effect, but more of a lens effect, is you get this kind of rainbowy edge to pictures. This is chromatic aberration. So once again, I mean, the short to all these aberrations is using different combination of lenses to kind of account for this. So there's no real, I mean, it all depends on the type of aberration really in terms of the type of lens, whereas the other cases we had specific, you know, ways to fix it. But point being is that sometimes you get these rainbowy effects when you have this chromatic aberration. So chromatic meaning that you have different colors. So this is a more subtle example. So you can see this is like a highlighted tree branch. And you can see that if you take a chromatic aberration, so it's not a perfect rainbow, but you can see this red edge and a blue edge right here. People who do photography can actually edit this out and make it look like this on the right here. So that's like what a chromatic aberration is when it comes down to that. So you can also, this is just showing you the type of rays that actually enter the eyeball. It's only visible light right here. We don't really have indigo or violet or ultraviolet light actually coming into our eyes, or infrared. These are the only type of light rays that actually get into the eye and actually refract as they do right here. So anyway, just a brief lesson about the human eye and how it works, and how you can take the lesson on lenses and apply it to something pretty applicable such as your eyes.